All right, welcome back. In this video, we're going to take a look at how we acquire, configure, and compile the MonkeyListen software. So, in the other projects, for example, the Monkey Jam, I always have a video on how you grab the software, and I kind of step you through it because I understand that sometimes when you get example code, and especially if you're new to embedded systems, it can be very difficult just to kind of understand what's going on. So. The purpose of this video is to show you where the source code is at, how you get it, and how you set it up without a whole lot of hassle. So first thing is you'll notice I am on the GitHub website for MonkeyListen. So if you just go to GitHub and search MonkeyListen, you'll find this page. And we'll bring you main GitHub page. Now, if you're not familiar with the Git version control system or GitHub, now's a good time to get familiar with it. But if you're not, the quick overview, version control systems are just ways to store your code and track changes. So whenever you're working on a project, especially a project that may be distributed among many people, you want to kind of keep a history of all the changes in your source code. And, there's nice tools to do that. GitHub allows you to use the Git version control system, and it's basically a nice interface to store all your programs and kind of host things on the web, and it's very social. It's a way to kind of get your stuff out there for other people to use, and it's free for open source projects. So you don't have to learn how to use GitHub to get the software. I've created a release for the software. We're currently at release R0. There may be releases in the future if we discover any bugs or add any features, but this video is on release R0. I'll try to keep the changes to a minimum so the videos are somewhat continuous, that the source code won't look all that different. So what we're going to do here is we're just going to grab the source code, a snapshot of R0, and there it's downloading. So I've got the folder unzipped on my desktop here. Let's take a quick look at it. So the first thing I want to point out to you is that in this project, there's actually two projects. There is the actual MonkeyListen software, and then the Simsys DSP library version 3.2. So for MonkeyListen to compile, you need both projects imported, into your CodeWarrior workspace. So first, I just want to navigate really quick. Let's look at MonkeyListen, and we'll go under Sources. And really, for MonkeyListen, there's just going to be a main.c. You'll be able to look at like the graphics driver for the screen and everything, but most of the magic is in main.c. So there's the files. Let's go ahead and import them. All right, I have a fresh CodeWarrior workspace. So what we can do is, there's many different ways in Eclipse. Remember, CodeWarrior is just uses the open source IDE Eclipse. So I'm just going to right-click and say Import. I want existing projects into Workspace. And it wants the root directory. So there isn't one project file. Actually, you got to import a directory of stuff. So I'm going to just paste in. I already had it ready to go. The location of R0, and what Eclipse does, it just parses through the folders and looks for all the valid projects. So I'm going to do that, and it pops up too. Simsys DSP 3.2 in the MonkeyListen. So let me grab, I want to click those. I want both of those. All right, so those are imported. Now, sometimes you do get a warning saying there's an invalid project path. I have a path problem in my project setup where it's looking for something on my local machine. You could ignore that. We're going to see in a minute. It doesn't really matter. So the first thing I want you to do is, before we go any further, is we're going to do a project clean. So this is going to remove all the object files and any binary files we have. And I'm going to say clean all projects. Just for good measure. Now, the first time it's going to build the project here, it might take a little bit because it has to build the DSP library, and there's quite a bit of stuff in there. But subsequent changes to the Monkey Jam software will not require a full rebuild of the DSP library. unless you're going in there and playing with something where you don't really need to. Everything you need is in the library. Just don't clean it on accident, or else you have to wait. All right, so it looks like it's all done. So what I'm going to do is I'm going to go over to the MonkeyListen and then click on main.c because everything we want is in here. So there's kind of two modes, and it's not in this video, but on the YouTube playlist that has all the videos for the MonkeyListen, I have a couple demos of these modes. Just I didn't want to, try to do them in the middle of this video. I gave short little videos of how they work, but here I'm going to show you how you compile them. So there's a short configuration section to the code. And so what I do is use some preprocessor macros to kind of control what's compiled. Now, you may or may not be familiar with preprocessor macros, but they're kind of neat. So we can have in C a macro called define, and I define a mode. For example, spectrogram is 0. Well, we can kind of use this variable later to control if we want certain things compiled in or not. So I've defined two modes. I have one called spectrogram, and I have another one called time domain plus FFT. And the mode I selected, I just create a third symbol that I define it as one of the other two. So for example, I have mode spectrogram. So if you wanted the time domain plus FFT, you put it in there. And then if you don't pick either one, just funny things are going to happen. The other thing you have to do is pick a sample rate. Now, I haven't looked at the upper bound here, but I found out 8 kilohertz. That may sound kind of low. It is for audio reproduction. But here, if we're just trying to visualize audio, especially if it's voice and or maybe looking to guitar or something, we're using 128 point FFTs. So we want to kind of spread our usable range on the low end, and it gives us a really nice visualization. So you can play with this number. I picked 8 kilohertz as a start. And so let's go down through here. So I put nice labels for kind of big sections of code. So I kind of showed you the audio ping pong buffer. There's going to be a separate video on how ping pong buffers work. I set up the variables for that. I need some buffers for the DSP, the FFT routine. Needs a place to store results. I need a place to store my windows. The systic timer is used for all of the audio recording. I trigger the analog to digital converter from the systic timer. So all that code is in here. We're going to come back and look at how it works in a minute, but I'm just kind of paging through the code. Then lastly, we get down to the actual main routine. Now, the first thing you'll notice in the main routine, I'm using a preprocessor statement called pound if. Now, you may have never seen this, but I'll show it to you. It's really neat. So if there's ever a time you want to control if something is compiled in or not, depending on some expression, you can use pound if. So here I just say if MonkeyListen mode is equal to time domain plus FFT. Well, if that's true, whatever's between pound if and pound end if will be compiled in. It's kind of like if that's enabled, the code will be there. If not, it's essentially not there. It's not compiled in. Now, a nice feature about Eclipse, it has an indexer that goes through to look at all of these symbols, and it's figured out that MonkeyListen mode is not equal to time domain plus FFT, so it's highlighted in gray. So what this means is it's a nice way of showing you, even though you see this code here, because it's highlighted in gray, it's not actually compiled in, because I don't need these variables in this mode. So let me step down through here. I need a couple variables for my FFT instance. Now, I'm going to have a separate video discussing a little bit about the ARM FFT function. For now, we're just going to see that, yes, we need this instance variable for a real and complex type. And there it is. The next section of the code initializes ports. I get the crystal the PLL running at 50 megahertz. I have a section of code that just gets the analog digital converter running. I have to initialize the graphics driver for the screen. Next, I initialize my buffering scheme, my ping pong buffers. And lastly, the next thing I do is initialize the FFT. Now, this is a canned function from ARM. All you have to know is kind of how to use it. And like I said, in this video, I'm not going to go into depth on how it works other than, we have to initialize our real FFT sequence. And here, as I set it up for 128 data points. The next operation I do before I get into my main loop, I start the capture buffer. And lastly, I notice how I have another one of these preprocessor, if statements. In this case, if I'm in spectrogram mode is kind of special, in that the way it draws the screen, it's only drawing one sliver of the screen at a time, meaning the column all the way to the right. And so to do that, I put the display in a certain mode where all I'm doing is every time I write to the screen, instead of incrementing pixel by pixel in a row, it increments in columns. So that's what they're for. So here we have our main loop, or while one, and to make everything work, there's a couple options. The first one is when I get to this point of code here, it means I have a capture buffer ready, and I got to figure out what I want to do. Well, the first thing I do is I have a jumper on the board, and in some of the demo videos, you see me playing with this jumper to enable or disable a window. So the only thing a window function is essentially an envelope you apply. So what I do is I take the active buffer and multiply it times my handing window. Now you notice I do two things here. I promote the active buffer to a Q31T type, and then finally I shift it to the right by 15. So this is a standard way of doing a fixed point multiply. Now, if you haven't watched them already, to understand what this code's doing, I have a whole series I included in the playlist on how fixed point numbers work. And in specific, I have one on, like, for example, the Q31 data type. In this code, most of what we use is the Q15 data type, but the concepts are the same. So make sure you go through the fixed point series of videos. But all this does, it goes through, it multiplies our signal by the window to window it if the jumper is enabled. Now, in my code, in this mode, I enabled spectrogram mode. So notice that this preprocessor macro, MonkeyListen mode, it's not true. We're not in time domain plus FFT, so it grays all this code out. And that's kind of a neat little thing. We'll come back here and look at it. But let's look at the spectrogram code. It's not in gray, so it compiles. So the way the spectrogram works is that I compute the FFT, and what I have to do is give it my FFT instance, the buffer of data, and then the results. All right. So before we do that, I should say after we do that, once we do this computation, we have to scale the results. And in the video where I discuss the ARM and how the FFT function, the ARM, for fixed point to work, it has to do some scaling to your signal before it does the processing. So the output of this is actually not in Q15 format. It's in a different format, and we have to rescale it. Once we get the data, then the next thing we have to do, the FFT function returns real and imaginary values. And in the introduction to FFTs, I discussed, that's what the transform produces. But in the case of our display, the real and imaginary data, what they do is they show us they give us a number that shows how well correlated our input signal is to a sine wave and a cosine wave, essentially 0 and 90 degrees. Well, for us, we just want to see how well we're correlated with a sine wave in general, and the way you do that is you look at the magnitude. So what I do is there's an ARM function for calculating a complex magnitude, and the only thing you do is feed in our FFT data, but we need a buffer for the result, and we've got to tell it how many points there are, 128 points. All right. Now, one thing that's important before I go any further is that the FFT function that the ARM computes right here is done on real data, And it's also done in place, meaning it uses the buffer you give it and actively manipulates that buffer to do the computation. It doesn't create a new one. And that's not stores the results in a new buffer, but the input sequence it plays around with. So you cannot feed this an array of constant data. Like, let's say you put in a sample data set in Flash. You cannot use it because the chip absolutely needs to use the input data and kind of shuffle it around. So it actively uses that data. And that's another reason why we need what's called a ping pong buffer. We essentially need two buffers, one for recording our data in the background while we can operate on the old data in the foreground. All right, so after we get the FFT, what we end up with is another array of data called FFT magnitude. All right, simple enough. Now, what we do, because we have 128-point FFT, really only, I should say 64 of them are useful. And the reason is because we produce the complex conjugate with the FFT. So all I do here to display the data is I have a command for the display that says start at column 63 and end at column 63. So when I write data, it's going to start writing at column 63, the column all the way to the right. What I then do is I loop through 64 points of magnitude. I rescale the data again. And the reason I do this is that we have a Q15 data type. That's like 65,000 different, kind of points. Well, this display, this New Haven OLED display, only can display 16 colors. So what I do is I heavily scale down, divide the signal to look at the upper portion, and then I clip the signal as well. I look at each point, and then I say if it's greater than my max value, set it to my max value. So this kind of gives me a 16-layer kind of gradation in intensity. And then the last thing I do, now this is kind of a tricky thing, and I really wanted to go through this to explain it, is that this display is 128 points wide. But when you write the data, since it's a 4-level intensity, for each column you write 8 bits. The highest bits is one column of 4 bits, and the lower 4 bits are the other column. Well, the way the display works, the only way you can scroll it is that it scrolls byte-wide, meaning 2 pixels at a time. So because of this, when I write pixel data to a column, I actually write 2 pixels at a time, and I give them the same value, and I effectively turn this display into a 64 by 64 pixel display. And that was just kind of a way of getting around this issue of scrolling, because if not, we would need another buffer to kind of work everything out. So this line of code, all it's doing is taking the lower part and recopying it into the upper part. So we just essentially make a wider pixel that's 2 pixels wide for each FFT value. After I kind of, in this display buff, calculate what that column should be, I write it out to display, and then I scroll the display to the left. Because I'm writing it all the way in the right, I want to scroll it over. I do have a corny little delay loop. This is not the best way to do it, but it is a way of doing it. Just a for loop, because if you run it at full speed, it moves so fast you can't see it. So I slow it down a little bit. All right, that's easy enough. So after we're done with displaying the data, then what we do is we sit there and wait for the capture active flag. So what the capture active flag is doing for us is actually something that is in the background routine, is that while capture active is true, what I'm doing, what that means is that I'm actively recording data from the A to D converter. So let's see, if capture active is a 1, what do? Well, we write our result from our A to D converter to a back buffer, we increment a sample. If our sample is less than 128, meaning we're calculating 128 points at a time, we have to start another A to D conversion. But what if our capture sample is equal to 128? What that means we're all done. So I reset this pointer called current sample and capture active to 0. So what this background routine effectively does is that while operations are going in the foreground, we're filling up another buffer of 128 values, and then we set this flag called capture active to 0, or I'm sorry, clear it when we're all done. So in our code, we sit there and wait while this is high. That means that we got the processing done faster, than the back buffer recording process could, finish its operation. So we wait for capture active to go low. And this variable, just so you know, it is declared as volatile. So the C compiler will ensure that it gets read every time. Then the last operation we do is we switch the buffer. So because I have kind of two operations going on at one time, one I'm trying to record data, and the other one is I'm trying to process the FFT, I need two buffers. And to implement this buffering scheme, we use called a ping pong buffer. And I'm going to have another video explaining how a ping pong buffer works. But in this code, all I do here is I determine which is my active and which is my back buffer, and I swap them. Now, the last thing I do is, now that I've swapped the buffers, I've used that back buffer, and I just swap it. Or I'm sorry, I don't swap it. I turn the foreground or the background processing back on by setting this to a value of 1. And then once I do that, I just loop back up to my while 1, and I keep looping. So the total process here are, I see if I have to compute a window. Once I compute the window, I compute the FFT. Once I compute the FFT, I display the data. Once I display the data, I wait until I have to swap the buffer for a new one, and then I'm done. All right, it's easy as that. Now, let me just turn on, and I'll just comment out this code, and we'll see this work here. I'm going to save this. In time domain plus FFT, I'll go through this real quickly. The loop is very similar. Now, you noticed already that the scanner, the indexer, figured out that I'm in FFT mode, so it brings these variables back. And so the main loop routine works almost the same as the spectrogram routine, only I kind of change how I display the data. First, I determine, do I have to display a window? All right. Or I'm sorry, do I have to compute the window? So the next thing I do is see the state of the FFT. If I'm not computing the FFT, well, that's the easy case. The only thing I do is draw the data. To draw the data, I use a graphics library that I clear the back buffer. I loop through 128 values, and then I just kind of draw lines between all the values. And that's it. And then once we're done, we dump our back buffer to the front screen. This graphics library, just you draw everything to the back buffer, and then you dump it to the screen. And that's as simple as it for time domain mode. Now, for frequency domain mode, for FFT mode, I clear the graphics back buffer. I compute the FFT the same way I did it on the spectrogram. I have to scale the data before computing the magnitude again. I compute the magnitude because I have real imaginary values. Then the only thing I do is then I draw lines on the screen. So because the first 64 magnitude values are useful, the other 64 are the conjugates, I just loop through and kind of draw 64 values. And you can see all I do here is I draw a vertical line, and I start at the bottom of the screen, and I draw up to the magnitude divided by 256. All right? And so that just draws my vertical lines, and then I dump the image to the screen. And that's it, folks. That's all there really is to the software. It's just a loop that kind of loops through, grabs data, does the computations, and dumps to the screen. So I hope this is useful for you. So now you can kind of compile and download the software. Oh, actually, I should show you that. Let's just look real quick. Let's go project, build project. I'm sorry, I forgot. We actually need to download it just so you can see it happen once. Now, just in case, in some cases, when you bring in the project, you might not have a debug configuration. Let's just make a new one. I'll click on Debug Configurations. And let me pull this over here. I'm just going to go Code Warrior, and I just said, oop, I'll just delete these so we might have them. Let's double click on Code Warrior. So it makes a new connection for us, or I'm sorry, new configuration. Here's the project. It automatically found the application, the ELF file. That's our essentially our binary. The only thing we have to do is pick the SDA. All right, we need open SDAs or debugger. Then we hit debug. Now you can't see it because it's sitting on my bench here, but this thing's going to kind of crank away here and launch. So here's downloading. All right, and we can hit go, and I can see in my window here I've got the FFT displaying, and there it is. So, all right, I hope this was helpful for you. You kind of saw the software and kind of got how it works in a nutshell. So take some time to study the code further and watch all the other videos. Have a nice day.